Hi, everyone. First of all, thank you to everyone for showing up. I'm Gustavo. I'm a lead data scientist in the digital innovation team in EDF R&D. Digital innovation, what we do is that we are on the lookout for all the new emerging technologies, trying to understand how they may impact the energy sector and how to leverage this to help EDF. So today I'm going to talk about how we're using computer vision for remote inspection of energy assets. And I'm going to begin by setting up the context, just a few minutes, and then I'll directly deep dive into a case study of how we use computer vision for inspecting wind turbines. And I'll conclude with some perspectives. So as you are aware, EDF has a lot of energy assets to support generation of low carbon electricity. However, it is important to ensure the safe operation of this type of assets by doing scheduling maintenance and constant monitoring, making sure that they are operating in a secure way to guarantee energy supply. So a few things could go wrong depending on the type of energy that you're producing. For example, solar panels may develop cracking and erosion, from exposure to the elements. In nuclear power plants, you have graphite bricks that help regulate the fusion process, and these may develop cracking and suffer from weight loss, where they lose mass over time, which may also hinder the operation of the plants. And for wind turbines, well, once again, they are exposed to the weather, to the elements, and there are a bunch of things that could go wrong, including things like cracks, erosion, lightning strikes, etc. And this last one is the one that I want to focus on for today. So wind energy is a key part in the strategy from EDF Renewables. So there's currently 13.8 gigawatts of gross installed capacity globally, and 70% of these ones, 74% of this one is wind energy. Currently in the UK, EDF operates 37 wind farms, and there are another 58 wind farms in France. And it is not only EDF that is relying on wind energy to supply low carbon electricity. Governments are aware of the importance that wind energy is playing in the migration to renewable energy sources. As part of the British energy security strategy, the UK government has set a target of 50 gigawatts of installed offshore wind capacity by 2030, while the numbers in France are 40 gigawatts by 2028. So as you can see, because there is a lot of, because this is an important part of EDF strategy, it becomes essential to protect its infrastructure by constant monitoring and schedule maintenance to ensure the efficient production of zero carbon electricity. So how do we do that? Well, we have to consider that wind turbines are really, really big, and they are getting bigger. So in the past, it used to be that you would set someone to climb all the way up to the turbine and then inspect the different sizes of blade, looking for different type of damages, some of which are shown here on the screen. However, of course, this is very risky. It is very costly because you have to pay a lot of money for someone to do that job, and also very time consuming. So nowadays, that's not, they don't do it that way anymore. Nowadays, we have remote inspections where you would take photographs of the different parts of the blade via different methods. This can be either ground-based photography or by using drone inspections. So in here, you remove the risk for the human, and instead you end up with photographs of the blades, which you can then inspect and look for damages. However, this is still not an ideal scenario because these are very high definition photographs, and you have to take a lot of images with some room for overlap to correctly cover all the sides of all the blades. So what ends up happening, there are approximately 300 images per turbine. So what ends up happening is that you come back from these inspections with thousands of high-resolution images that now your engineer has to sit down and look at them and inspect one by one, looking for this type of defects. It takes approximately 4 hours for an engineer to look at the images from 3 blades. So of course, this is a very time-intensive task. It is tedious and repetitive, and it is also subject a little bit to subjectivity because each engineer may see things a little bit differently. So needless to say, this is not the best use of time for your highly skilled blade engineer. So what we set out to do in this project is we set out to build a computer vision system that can automatically scan the images from these remote inspections and can detect and highlight different type of defects such that the engineers can automatically focus on the type of defects that matter the most. Here, I'm showing a broad overview of how this is achieved. And this is mainly through the combination of 2 steps. One is a background removal part to remove the background to reduce the confusion that may appear in the predictions and therefore reduce the risk of false positives. And another one is using an image segmentation model using deep learning to identify and highlight the different type of defects appearing in the blades. This is a high-level overview, but now let me quickly take you through how this is developed from start to end to give you a little bit more insight on the different aspects we have to pay attention to. The first thing we have to consider is what type of data can we use to train such type of model. Well, of course, we need inspection data, and luckily for us, we had a large history of images from previous inspections that our engineers have already looked at. We had two main sources of data. One of them was inspections from a company called SkySpecs, which they use drones to capture the different angles of the blades. And as you can see in the images shown in here, you can have a wide variety of backgrounds, including some dirt, some roads, some grassy fields, and in some other cases, you may even have snow, which may make it difficult to distinguish the blade from the background. These are high definition images, and the most common type of damages that appear in here are cracks and erosion. The other main data source is from another inspection company, Cornice. This is mainly for inspection in our sites in France. And here, the main difference is that this is a ground-based photography. So now the background is mostly just the sky. This simplifies the problem to some extent, because most of the time, what you're going to see is just going to be the sky. However, it may still be difficult because in some cases you will see a cloudy sky where the background is just a white or gray, which may also make it difficult to distinguish the blade from the background. As you can see, this is once again very high definition images. And as noted before, the most common type of defects appearing in here are cracks and erosion. So our engineers asked us to focus on this type of defects in particular, which was the main part of our attention. Now, in the past, the engineers have looked at these images and they can tag where in the image a defect is appearing. However, they didn't necessarily have in mind that someday one person may have the crazy idea of using these images to develop a computer vision system. So one of the main challenges we faced was related to the quality of the data. Some of the annotations made by the engineers, it may be good for them, but they are not necessarily the best for training a machine learning model. Here I'm showing a few examples of the different type of images that we may get. And I want to draw your attention to the case on the top right, where we have a very large bounding box, where the engineer has grouped a lot of small defects together into a big box. Now, you probably cannot see it because the image is so small, but if you were to zoom in a lot, you would see a lot of very small faint cracks. These are known as fatigue cracks. And in this case, because they are appearing all together, the engineer just decided to put everything together. However, in this type of cases, this is not very good for training a machine learning model because this may lead to a lot of confusion. So we have to be very careful on analyzing the type of images we had and excluding those that we thought may not be suitable. And more than that, we even had to do some re-annotation on a subsample of images. And here I'm showing examples of what the original annotations were and our proposed annotations for training the model. And just by running a quick experiment, this immediately showed the importance of the data quality because we were able to see a very marked contrast in the performance of our model. So this is just to say that as in any application, data quality is one of the most important factors determining how well your model can perform. Now, I also mentioned before a little bit about background removal. And what we noticed when we were experimenting was that some cases the model will get confused due to the texture or the things appearing in the background, and will have some false positives. So in order to reduce this type of risk, we decided to also train a background removal model to separate the blade from the background. And after trying a bunch of different things, what ended up working the best for our case was using this model called a tracer, which basically does image segmentation and is using a combination of silent object detection with an attention mechanism. I think this model was proposed in 2021 or 2020, so it is relatively recent. And we observed that, yeah, for our application, as you can see on the screen, it is doing a fairly good job of getting only the main part, the foreground, which is the blades. So that was one route doing the background removal. Now, I want to talk a little bit again about the type of defects that we may encounter, because it is important to understand what type of defects we want to detect in order to develop the actual model. And here I'm showing a few examples of the different things that we may find all in a single image. So as you can see, some defects may be very obvious, like this very long, dark, thin crack that is appearing here, while in other cases, they may be much more subtle, like the much smaller cracks that are shown in the other rectangle here. Now, this is also a challenge because this is telling us that not only do the different type of defects look different from each other, but also within the same class, cracks can look very different from each other. So we have to take that into consideration. And another thing is that normally when you think about detecting something in an image, the first thing that comes into mind is object detection, where you would normally use bounding boxes to identify different elements. And we tried this initially. However, we quickly realized that this doesn't work in any case, and this was not the ideal route in our application. In here on the example that I'm showing on the bottom right, the dashed line represents what the bounding box would be for the erosion defect showing in the edge of this blade. And as you can see, the actual area of interest is probably less than 3% of the area of the bounding box. So instead of going for object detection using these bounding box annotations, we were forced to use polygon annotations and instead pursue an image segmentation approach. This actually turned out to be very good, because then in this case, what the model is going to predict will be not just a box containing the defect, but also the actual shape of the defect, which, as you can see from the examples that I'm showing here, they can appear in very irregular shapes in different type of angles. So putting these things together, we tried a lot of different approaches, a lot of different models. We did a lot of benchmarking and a lot of optimization. And after a lot of hard work, we are now currently at a state where we have a model that works reasonably well on detecting these different type of crack, erosion, and other defects, and that can highlight the shape of the defects on the images for each individual case. Uh, in some cases, if a lot of small defects appear very close together, they may appear as, they may be grouped together, such as the case of these rectangular boxes that I'm showing in the middle. However, if there is some sufficient space between the defects, the different type of defects can be tagged individually. And each prediction is accompanied by a confidence score that can help our engineers to focus on the ones that they want to inspect in particular. And the important thing of combining these two type of data sets was that we wanted to have a solution that can work for diverse type of backgrounds. Because as I mentioned before, sometimes we may have a view of a grassy field or the forest behind. Some other times we will have the sky. And I don't know, maybe next year we will work with a different inspection provider that will take images in a different way. So we wanted to, it was very important to incorporate this diversity in images to achieve a model that can have a good generalization power. We believe that this is very valuable for our engineers because we are able to precisely outline the shape of the defect, such as in this case where there was this line, this crack growing in this strange L shape. And it is impressive that we're able to, I am amazed that we're able to finally highlight something like this. Of course, this has not been easy. This has been a project that is going on for several years already, and we are now in the final stages of development, and we're very close to deploying this model so that our engineers can actually start using it now. So we believe that this will create a lot of value because this is going to help our engineers save time. Now, a large volume of images can be immediately discarded from human review, those not containing any defects. And for those that do, the engineers can look at the confidence score attached to each defect so that they can focus on the ones that require the most attention. So, of course, the goal was never to replace an engineer. Instead, the goal is to create a tool that will help them make their life easier. So, so this is mainly what I wanted to share today, and I wanted to conclude with a few perspectives. Oh, sorry. So what happens next? So now we have a tool that more or less gives you where the defects are in an image. Next, you may ask, okay, how are today's defects going to evolve tomorrow? And one way that you could maybe think about this is by considering digital twins of the wind turbines. So we can feed in the predictions of where and what type of defects are appearing in the different parts of the blade. You can feed this into the physical model and evolve this over time to understand how your defects are going to evolve. Now, of course, wind turbines is not the only application for computer vision and remote monitoring. There are a lot of very interesting things that we can also look at where this can play an important role. I added here just a few examples just to write something. For example, you can do something similar for monitoring solar farms. Another very important application could be understanding coastal erosions. So a lot of our nuclear assets have to be on coastal areas. And we know as a part, because of climate change, this has an impact on water levels, vegetation, and environmental conditions. So it's important to understand how this is going to affect our nuclear sites, and similarly for site condition monitoring to ensure that our infrastructure is safe and the people that work at these plants can continue doing their job safe in a secure manner to to support the generation of low carbon electricity, as I mentioned before. That's pretty much what I wanted to share. wanted to share today.